Hi, everybody. Thanks for joining in. We'll get started in about 2 minutes to give folk a chance to get connected and all set up. Thanks for your patience. Let's give it just another minute or so for folk who might be trying to get to us this evening. Thanks for your patience. We'll start in just a few minutes. Sorry, so could somebody kindly unmute and let me know if you're seeing the sharing that I'm doing with the homepage?
Yeah.
All right, thank you very much. So before I jump in, I just wanted to remind you that I have been making available to you. Yeah, the videos for our class meetings. In the event you're not able to make it, or if you want to go back to review for clarity, or for any reason, you know, the videos for our class meetings are always available in the announcements. I had a few students reach out to me and ask where they could find the class recordings. So, you know, just as a reminder, they're always available out here in the announcements. All right. So before I jump into tonight's material, let me just open up the floor and ask if there are any questions. Last week, our coverage dealt with unit conversions, and I worked quite a few examples for you dealing with unit conversions. And if my memory serves me correct, I offered the opportunity to share out, to allow you to share out a sample problem dealing with unit conversions that you might have done or found in some in notes or in textbook. Got an open mic, please mute yourself if you're not speaking. Thank you very much. So as I was saying, so, you know, to encourage participation or engagement, if you will, I offer the opportunity for students to share out sample unit conversion problems that you might have worked on or came across besides those that I did, right? So you are tasked to find an example of a unit conversion problem or make up one, work it, and then bring it back today and I would allow you to share it. And you know, we could take a look at it that way. If there's anybody who's open and willing and wanting to engage and share any unit conversion examples that you might have worked out, just let me know. I'll stop share and give you permission to share, and then we'll take a look at your sample problem, just as a way of, you know, wrapping it up, putting a bow on it, and saying, here's this unit conversion practice. Anybody? Okay. Well, that silence tells me that I don't have any takers. So that silence also tells me that nobody here today will be getting the bonus points that I would have given if you had shared out. I don't always announce ahead of time things are bonus, but for those brave souls that step up to the plate and are willing to share when I ask, you know, or allow those opportunities, or ask specific questions that, you know, I want the class to be engaged with answering, as a way of review, as a way of practice. I sometimes award bonus points for those things to kind of keep you on your toes, so to speak, and reward you for being, you know, active and participating in our sharing of materials. I always tell students, this is not just a one-way thing. If all we're going to do from 5:30 to 8:30 or 8:15 or whatever time we leave is listen to me talk, this is going to get boring real quick. Okay, not just for you, but for me as well, because I go into what I like to call robot mode, where I'm basically speaking from memory, right? It's like I've memorized the speech and I'm giving it to you to share information on the material, as opposed to us creating opportunities together where we can engage one another and you can share your thoughts and your ideas and your examples and your questions with me and the rest of the class. Okay, that's really the environment that I would like to have in here, so that it becomes more lively, right? We aren't face to face, and so the tendency is to say, you know, my camera's not on, I got 5 other things I have to do, I'm just listening, you know, and now I don't have any questions. But then when it comes time to do assignments or take tests or exams, then students start to realize, man, I really did have questions about that, or I'm not sure how to do that, or yeah, that wasn't clear to me. Now is the time to engage with me so that we can clear up any questions or misconceptions that you might be having about this material. Okay, so I just want to put that out there. And as I say, that's my 2 cents for the day, and I'm gonna stick to it. So before I start talking about 1D motion, unit conversion business, you know, bonus opportunity gone, are there any other questions that you would like to ask me before we jump in? I see somebody put something in the chat. Let's see. Number 4 on problem set number 2. John, I respect that you have a question about that one. How about you and I tackle that one together? Because typically I don't work problem sets questions in, you know, like out in the open forum with the class. Those are homeworks. And if you have a specific question about it, we can take care of it one-on-one. But you know, I'm not one of those instructors that, okay, let's work problem set number 2, question number 10. No,
I get what you're saying. I didn't think about
yeah,
it.
because basically what I'm doing is giving away the answer,
Yeah.
right? And I don't want to do that now. But we can talk one-on-one. And you are more than free to approach me about this same question after I'm done, before kind of like one-on-one, if you want to say that, right? Is that okay?
Yeah, sure.
Yeah, okay. So yeah, because I've been in classes where the instructor gives homework and those are the examples that they do. Well, that's not going to help me. Work some different examples and let me try the problem sets on my own. Right. So, okay. Any other questions besides, the obvious work my homework for me? I'm not picking on you, John. I really do appreciate you being brave enough to ask the question. All right. So let's get into this 1D motion business. Okay. So up till now, we hadn't really been dealing with the idea of motion. We've been focused on things like units, right? Because all of the stuff that we need to understand in this class, including motion, utilizes measurement. So the scenario that we're facing now is we have an object that's moving, and we want to be able to describe that moving object, that moving object's motion. I don't want to describe the moving object like it's blue or it's green or it's big or it's small. Those terms are relative. Different people will think differently about them. That's a kind of a qualitative thing. But what we do want to do to describe that moving object is to give a quantitative description based on measurement for certain aspects or properties associated with that motion. That's what we want to be able to do. And, that's a big chunk of what we want to do in this course. And so we're going to start off describing objects that move in the simplest fashion, if you will, and that is 1D motion. 1D motion meaning the object is moving in a straight line, and we want to describe certain aspects of that motion. Okay, and so you can see from the objectives the kinds of things we'll be looking into as we, describe the moving object. What kinds of things do you want to know about this object's motion? Well, we want to know things about, first of all, what are the requirements to know that the thing is even moving? I mean, if we say an object is in motion, the question is, how do we know that? Okay, and we'll see what are some parameters and things that must be present in order to establish that, in order to answer that question. We'll be looking at properties like position, speed, velocity, and acceleration. Those are the kinds of properties that we want to measure for our moving object. We'll be looking at distance. And in particular, we'll be looking at the difference between a property called displacement and the property distance. Remember, in this class, the things that we measure, we give them the label properties or quantities, things that can be measured. We can measure the position, we can measure the speed, we can measure the velocity of our moving object as a way of describing its motion. We'll look at the relationship between those various properties, and especially as it pertains to the various mathematical equations and things like that that we can utilize to help us understand that moving object. We'll look at, we're going to watch a video and that deals with motion graphs, because outside of equations, outside of mathematically describing our moving object. We can also use graphs as a way of describing the motion of our object. We'll look at a particular type of motion, free fall. We'll understand what is free fall, and then how do you use the understanding of free fall to solve problems regarding the motion of our object. And so, when we finish with this overview, you should have a foundation, some basic concepts down that are relevant for 1D motion and that will carry over into our coverage of other types of motion. So the things you're learning now, these definitions and concepts, they're definitely useful for an object moving in one dimension, but they can also be utilized to explain the motion of to quantify the motion of an object that is moving in more than one dimension. And we'll start looking at those types of motion as we move along. In fact, we're going to look at a whole lot of different types of motion in this before this course is over. And all of it will fall back to, do you understand these basic concepts that I'm going to start you off with tonight? Understanding that these basic concepts are built on measurement that you learned for the past couple of weeks, okay? So you don't throw that measurement stuff out the door. The reason you learned it in the first place is so you could do this stuff. So what activities do you have on your plate for this week? And before I jump into talking about the activities here, I do owe the class a deep apology, a sincere apology. I graded some items last week, but I'm a bit behind on grading. I will be getting to that, your grading this weekend for sure. I've had a couple of major projects going on at work, and add complications of being ill to that. And so, I've been, I've been holding it together as best as I could for the past few days. But this weekend will be my time to play catch up and get some scores out there for you, so you have some sense of how you're doing so far. So I do apologize. Typically, I like to get things done on a weekly basis, but I'm a little bit behind right now. But I'll catch up. All right. So that being said, let's look at the things you do have on your plate for this Saturday. All right. So you've got a discussion that deals with 1D motion that you have to complete. Remember, for a discussion, you first have to answer the questions yourself, and then you are required to respond in a thorough, in an engaging way to two of your classmates, right? Something beyond, I like your answers, or we got the same thing. Imagine that you're sitting in a classroom together and you're working and solving and answering those discussion questions together. You wouldn't just say, yeah, I got the same thing, or I agree. You would have a discussion on, well, how did you do that? Why did you have to also include this, or you would have a much more of an engaging conversation than I like your answer. So for this discussion that's due Saturday, you have to do the same thing. Okay. As much as we can replicate the face-to-face interaction, we try to do it through the discussion. The other thing that you have on your plate is problem set 2. Problem set 2 is due by this Saturday at 11:59 p.m. as well. Now remember, for the problem set, this problem set number 2 actually deals with unit conversions. Okay, the discussion is always on the current topic. The problem set is always on the topic that we covered the week before. So since last week we covered unit conversions, this week your problem set is on unit conversions. Okay, so don't get confused by that. All right. Let me also caution you. And when you do a problem set or discussion or any assignment for me, the name of the game is show your work. Okay. If you turn in problem set number 2 and you don't show me how you got your answers, I won't give you credit. Okay. So be thorough in your responses when you're doing the problem set. Okay. There's information just below that on how you turn in a problem set to me. I'm still getting emails from students saying, I didn't see an upload box on Canvas, or I'm not real sure how you want me to send this to you. By now, you should know how to send me your assignment items. Okay. Problem sets get emailed to me, and you have to follow the instructions that I provided in terms of what types of files can you send to me. Okay. So I keep telling students the weekly overviews, the weekly overviews, the weekly overviews. I'm getting emails left and right. Where do I find this? I'm like, okay, you should have figured that out in week 1, but go check out the weekly overviews. That's where you find all your assignments. Okay. To help you complete those assignments, I've compiled some resources. I pulled chapter 3 from your textbook. And again, I put it right here in the overview, right where you need it. So you don't have to go looking through the book to figure out, hey, what do I need to be reading in the book to do this? Or what do I need to look at? It's right there. That's the chapter that deals with 1D motion, chapter 3. Okay. There are some 1D motion videos. And I got an email from a student this weekend saying, hey, when I clicked on that, there are a bunch of videos. Which ones do I watch? All of them. All of them. Okay. Free fall videos. You should watch those as well. Okay. The motion graph videos, if I can get the audio to play back, because I had some trouble with that the last time I tried to do it. The students could see the screen, but they couldn't hear it. I think I figured out how to make that work in this Zoom environment. So I'll give it a shot to see if we can, I can get that working, and we'll watch the motion graph videos together. But if I can't get the audio part to play over Zoom like I'd like, then you will have to watch that video on your own. And I'll just like there's a certain point that you could stop at, and then after that I don't really get into it. So if you have to watch them on your own, I'll make sure when I put the announcement out that I'll tell you, hey, when you get to this section of the video, you can stop. Okay. But we're going to try to make it work in here first. And then the supplemental notes, right? If you've been following along each week, the supplemental notes are my notes. All right. So I'm going to use those notes to explain some basic concepts regarding 1D motion. And then I'm going to go to the extra notes, and I'm going to utilize that to work some examples to show you the kinds of things that you should be able to do, and the kinds of things that you'll see on the problem set that you have, the problem sets that you have coming up related to 1D motion. Okay. All right. So are there any questions on the objectives, the activities, or the materials that I've made available here to you? All right, let's get into these notes. All right.
Not yet.
Not yet. Hey, I like that response because it means that you're going to be engaged. And if there is a point when yet gets here, you're going to ask me your question. That's what it means to me. Let me see if I can make this full screen. In this full screen mode, you can still see everything. Am I right?
I think so.
So you're seeing the screen that says Intellis Learning Open Courses?
Yes, ma'am.
Okay, great. That's what I want to make sure of, because I sometimes wonder, if the sharing works right when you go full screen, but hopefully that holds up. So, every time I go into one of these packets, I kind of remind you that you should be focusing on these, you know, trying to digest the material, and this is a good guide for that, okay? So this how to study this module reminds you of the kinds of things you need to be doing if you want to really learn and be able to apply this information that we're covering, okay? Yeah, I always tell students, there's no substitute for putting in their time. You are not going to learn this material through osmosis. It's not going to happen. You have to get down and get with it, you know, some sweat equity, you know, get with it, right? You have to put in the work if you want to understand this material. There's no way around it, okay? I always tell students the difference between you and me is that I literally eat, sleep, and drink. Well, when I was a student, literally eat, sleep, and drink physics, right? Now I know that, you know, that's not real, that's not necessarily realistic for many of you in the lives you have, but there still is no substitute for investing some time to really study this material. And it shows. I can tell the students who are really putting in the time when it comes to the quality of the work that they turn in for problem sets and the way they perform on exams. If you don't put in the time, trust me, my midterm is going to let you know. Okay. All right. So these objectives just remind you of the kinds of things we'll be covering in this packet that come right out of the objectives that are on Canvas. All right. So motion. What do we do? What do we want to know when we study motion? Well, the first thing is we need to understand the limits of what we're trying to do when we're describing a moving object. To start off with, we only want to do a kinematic description of our moving object. And that word kinematics, it means motion. Okay, that's a Greek word for motion. Well, it's derived from the Greek word. And so the important thing about giving a kinematic description of a moving object is you don't focus on the causes for the motion. You have no idea what caused the object to move, or why it's moving, or any of that. The only thing you do in a kinematic description is explain things like time, position, distance. You know, you don't focus on things like forces or you know, lift and air resistance and gravity. When you do a kinematic description, you study motion without respect to cause. Pure motion, no indication of the causes of the motion, okay? So we don't consider causes when we do kinematics. Okay, the object is moving. I don't care why, I don't care how, I just want to describe it. Okay. So we'll see what kinds of things you have to measure in order to give a kinematic description. Now, another limitation on what we do at this level of a course is that we can't analyze situations where we're dealing with 3 dimensions. Yes, we live in a 3-dimensional world, absolutely, right? But in order to adequately describe the moving object in 3 dimensions, we would need a whole lot more math than what we're ever going to touch in here. And so what we do is we focus on the simplest case, and that is 1 dimension. And so when you're dealing with 1 dimension, you only have to focus on things like forward and backwards, or left and right, or up and down. The object is moving in a straight line, and you want to describe that linear motion without worrying about what made the object move. Okay. So it's real important, that you understand the conditions that we're dealing with. The boundaries and limits on what we're able to do at this level, at this point. Okay, or at least what we want to be able to do, I should say. All right. Because otherwise, you could be trying to solve a problem that's way more complex than anything we want to get into in here. Okay. I sometimes see students solve problems and they pull out the trig and things like that. We don't do that in here. Okay. Simple. All right. And so if we're going to give a kinematics description, some of the properties that we want to investigate quantitatively are things like position, displacement, time, velocity, acceleration, distance, speed. Those are things that we want to be able to express quantitatively for our moving object, because if we can express those properties, quantities, then we have given a kinematic description of our moving object. Okay. Now, I mean, it's kind of inherent and you don't really think about it too much, but obviously if we're describing a moving thing, something's changing. Something's changing. Either its position is changing, its velocity is changing, most definitely time is changing, because we know that's the one thing that keeps moving no matter what, right? And so we have to get used to how we express this idea of change. And to help us with that, we borrow from the Greeks again. We borrow a lot of things from the Greeks in physics. We borrow from the Greeks again, their letter delta. We use the letter delta to express the idea of change. Okay. And so the way that works is that whatever property is changing, we put the delta symbol in front of it. So for example, if we're using T to represent time, and I want to know about how much the time changed, I represent that as delta T. If it was position, for example, and I wanted to know how the position changed, typically we use the symbol X for position. And if I wanted to know how the position changed, I would say delta X. Okay. So it's important, notation is a big part of this, right? I mean, you have to be using notation that adequately represents what you're trying to express. And the reason, that's why I'm, and you're going to be using this throughout the course. As long as we're describing moving things, you're going to need these things, these concepts. So let's get them under your belt, let's put them on your tool belt early. So as long as you need them, you can just, utilize them. Okay. Well, I said earlier that, one of the objectives is for this whole block of this whole overview is adequately providing information to establish that an object is moving. Right. So, what conditions have to be met in order to establish that an object is moving? Well, one of them is a reference frame. So if I ask the question of you, is your house moving? Somebody might inevitably say, no, my house isn't moving. And somebody might say, yeah, my house is moving. And then the question becomes, how did you determine that your house wasn't moving or it was? And so at a fundamental level, what's being dealt with there is the notion of a reference frame. If somebody says, is an object moving? The next question should be, with respect to what? Where are you measuring from to determine whether the object is moving? Okay. So we have to have if we're going to say an object is moving, we have to have a way of locating it. And the way of locating it, the way of establishing position is by establishing a reference frame. Okay. And so what we like to do is we like to choose our reference frame so that we simplify the situation as much as possible. All right. So when I ask the question, is your house moving? Well, it depends. Are you measuring with respect to Earth or somewhere else? Because if you're on Earth, with respect to the Earth, let's hope your house isn't moving. But if you're standing on the moon and you're looking down at your house, absolutely your house is moving. Because you have, that's a different reference frame. Okay. So that's why it's important to establish, where are you measuring from? What is your origin? What is your starting point? Okay. And they give the nice example of the airplane here in the packet. So you choose your reference frame. Choose your reference frame in a simplest fashion as possible. So for example, if you're a passenger on the plane, with respect to the plane, you are not moving. You're on the plane is moving, you're moving, but if we look at your position with respect to the plane, your position's not changing. But now if we look at your position from the viewpoint or from the reference frame of the Earth, then definitely you're moving, okay? So where's your reference frame? And choose it as simple as possible, okay? But no worries. We have some nice tools that can help us understand this idea of a reference frame. And we borrow from the mathematicians their idea of a number line or the Cartesian coordinate system. Okay, X and Y. A lot of you who've had experience with math, X and Y, and then you have your start point, that's the origin or your 0 point. Okay. All right. So once we've established the reference frame, the next question is, according to your reference frame, according to your origin, according to your starting point, is the object moving? Well, if the object's position is changing, then yes, it's moving. So think of it this way. The object was here, now it's there. Its position has changed according to our reference frame. And so we say that the object is in motion, and then we measure how much of a position change. That is called displacement. So the amount, the quantity that specifies how much of a change in position is called displacement. Okay. Now there's a counterpart that goes with displacement that is defined differently, and that's called distance. Displacement and distance kind of go hand in hand in some instances. Okay. This distance simply tells how far the object moved. Okay. So look at the two positions, any two positions, and figure out how far, and that's the distance. All right. And we need to be careful because distance and displacement aren't the same properties. And we have to be careful because you'll see in the example I'm about to discuss, they can be very different for the same motion. Okay. So you see in the picture here, they're using home as kind of like your starting point. So if a person goes from home to the store and you look at the distance they travel, it's 3 kilometers because that's how far they went. Displacement, on the other hand, because it requires you to say where the object is with respect to where it started, we would say 3 kilometers forward. Okay. Distance would just be 3 kilometers. Displacement would be 3 kilometers forward or 3 kilometers to the right, or 3 kilometers backwards, depending on how you're measuring. Where's your origin? Okay. But the idea for displacement is you have to say which direction the object is moving. Now, no worries for this, material that you're going to be getting into. If you do things correctly, the direction is built in. Okay. The direction is taken care of if you do things correctly. Okay. So you don't have to worry about right now, to the right or to the left or up or down. You just have to answer the question, correctly in terms of how you find displacement, and that'll be taken care of. All right. Let's take that example of home in the store and carry it a little bit further. Suppose the person went from home to the store and back. Okay. So in that particular case, it's very easy to see that the distance they travel is 6 kilometers because they went 3 kilometers one way and then 3 more kilometers the opposite way, but the total is 6 kilometers. That's how far they went. That's the total length of the path. Okay. Displacement, on the other hand, is a little bit different because displacement says if you go from home to the store and back, then your start and your finish are at the same place. So if you stop where you started, then your displacement is 0 because your change in position is 0. Well, you back where you started from, so you didn't displace any. Now, if the person went from home to the store and stayed there, then they would have a displacement of 3 kilometers forward or to the right. Okay. So now let me ask you to chime in with any questions you might have or comments that you want to share regarding this idea of distance and displacement and how they are different. Okay. So I'm gonna ask a question and see who's got the thinking cap on. So what scenario has to be present in order for distance and displacement to have the same size? See if you're thinking.
Can you say that one more time?
Yes. What conditions have to be met? What's the scenario that has to be present in order for distance and displacement to have the same size?
Can it just be not move at all or go the same, like go, I don't know how to explain it. Like if you move a pencil a foot away from where it was, and the distance is a foot and the displacement's a foot from where it was.
In terms of the size. And we're assuming that you mean that you're moving that pencil in a straight line. Am I right?
Right.
So if you move an object in a straight line and you move away from your starting point or your origin, and that's it, then the size of your distance and the size of your displacement will be the same, right?
Right.
Straight line motion, the size of the distance and displacement are the same. But once you turn around and start coming back, then they're not going to be the same. Your distance will have a bigger size than your displacement. And if you go all the way back to your start point, your distance is definitely not going to be the same as your displacement, because your displacement will be 0. Okay? Does that make sense to everybody?
Good.
Yeah, it's making sense. So can I just do it in a different way? So
Yeah, sure.
you know how France gave America the Statue of Liberty.
Mhm.
The distance and the displacement is the same, correct?
In terms of what? I mean, you said they
If,
gave
if
us
we
something.
went from a straight line from France to New York City, and where they put it is where it stayed.
Yeah.
The distance and the displacement are the same, correct?
Let's use the right language there. The size of the distance and displacement are the same.
Size. Okay.
That's a very important word, because they're not the same, because displacement has to have a direction. Distance doesn't. Distance just says how far. Displacement says how far relative to where you started. So in that case, let's say that France is further east than us, right? So in order to go from France to New York, let's just say that you moved a certain amount, let's say, southwest, right? You got it? Or let's just imagine straight west. So the Statue of Liberty is 2,000 miles west of where it started off from France. Does that make sense?
Yes.
Okay, right. And if France decides tomorrow that they want it back and they come get it and take it back to France, then the distance is going to be 4,000 miles, but the displacement is going to be 0. That makes sense to you?
Yes.
Good. I like the fact that you're somewhere in there, you're trying to process, like, what does this mean on the ground, right? Let's take it out of the textbook and let's talk real turkey, right? Like, how does this work in the outside of the magical Zoom room, right? So that's good, because when you can process things like that in your thinking, then it's going to carry you a long way when you get ready to problem solve. Because I always tell students, you can't solve problems if you really don't understand the concepts. Having to true understanding of the concepts is what will carry you when you're problem solving. Because the problems that you solve are based on these ideas and these concepts and these formulas. So, at some point the rubber meets the road, and you gotta be able to show that you understand. All right. And I like the fact that, like, you didn't you're not looking at this stuff from okay, that's physics and this is something else, right? Don't leave your experience at the door when you come in here. Don't. We might have to ask you to think deeper about your experience, but you have life experience that tells you if I throw the ball up, it's going to come back down. The physics is, let's describe that motion. Okay. When you know, like I had a student that told me if I, like if I throw the ball up, when it gets to its highest point, gravity cuts off. Yeah, you live on the planet Earth long enough to know that that's not happening. So you have to bring your experience to the table. Even if it means in the end, you refine your understanding of that experience. Okay, that's what you have to be open to. All right, so let's get a little bit deeper into this. How do we quantify this property displacement? You gave me a great example of the Statue of Liberty. How would we quantify that? Meaning measure, right? So we would, to measure the displacement, we need to look at what? Where the object started and where it stopped. Okay. And we use the symbol delta X because we're using X as position. So delta X means the change in position. And that change in position is what we call displacement. And in order to find the displacement, we take the final position minus the starting position. So see, you understand the concept of what is displacement. You understand how we express that in symbol form, and then you understand how to calculate it. All right. So to get that displacement, you take the final position minus the starting position. Okay. Now, it's easy to understand the X with the F as the subscript as final position. But, some students want, why don't you use a XS for starting position or XI if it's the initial position? A lot of books do use those kinds of notations. But the notation that you see here is typically what's used in, a great many books. The X with the subscript 0 is pronounced X naught. 0, that subscript 0 is not, meaning from nothing. Okay. In other words, where are you with reference to your starting position when you had nothing? That you could think of it that way. Okay. Or when your position was at the 0. Okay. Does it make sense to you how the formula for displacement?
Yes.
Okay. So now let's see how we can use that formula. Okay. So it says if an object moves from an initial position of 2 to a final position of 7. So imagine you have a number line. You have a number line, and that object is moving from 2 on your number line to 7 on your number line. Okay. The number line in this case is our reference frame. Okay. And so if we want to find the displacement, it says take the final position, which is 7, minus the starting position, which is 2. So we get 5. That's our displacement. Okay. What about if the motion was reversed? What if the object started at 7 and ended at 2? Started at 7 and stopped at 2. Follow the rule. What does it say if you want to find displacement? In that particular case, we have to say the final position in this case is 2 and the starting position is 7. When I say here final minus starting, that's 2 minus 7 or -5. And you may be thinking, a negative number. Yes, but not negative in the sense of less than, greater than. Okay. The minus sign in this case gives us direction. Okay. When you are dealing with a property like displacement, the negative sign is meant to give direction. Now notice, whether we go from 2 to 7 or 7 to 2, the size is still 5. But if we're going from 7 to 2, then our displacement is -5. And the negative sign tells me that I am now to the left of where I started or backwards of where I started. Okay. Or west of where I started. Okay. So be careful. That means you have to really understand the definition to calculate the displacement correctly. Now, of course, in the example, we didn't have put any units on it. So technically, that in the example, it could have been meters, it could have been miles, could have been feet, could have been yards, could have been, you know, kilometers, megameters, whatever. Okay. But typically when we solve these kinds of displacement and distance and kinematics properties, we rely on the metric system. And so the base unit for expressing displacement and distance is meters. Okay, so displacement and distance both use the unit meter. So if you look at the unit alone, that doesn't tell you what property you're measuring. You have to understand the concept to correctly know which property you're measuring, and then know that if you're measuring distance or displacement, the metric unit is the meter. Okay. Any questions on how you find displacement, how you find distance, or the appropriate unit for either of them? Okay, so I'm not going to go deep into this scalar and vector business tonight, because that is actually what we will focus on next week. I've already kind of let the cat out of the bag, if you will, with this notion of some things involving direction and some things not involving direction. And we'll take a look at that on a deeper level next week. For the assignments or anything that you have to do, you know, now, as I said, you don't necessarily have to worry about the direction, because if you approach the problem and solve it correctly, the direction will work itself out. Okay, so we're not going to worry about the scalar and vector business too much, but of course you can take a look at it. We'll get deeper into it next week. Okay, as I said earlier, when I talked about the 7 and going from 7 to 2 or 2 to 7, I said, imagine that you're using a number line. Well, see, we borrowed that from the mathematicians because the number line has a clear origin, 0, as you know, that we can use as a start point. And then if we're to the right of 0, we know it's positive. And if anything is to the left of 0, we call it negative, right? We could take that number line and you know, use it if in a vertical fashion, where we use the vertical number line to express up and down. Up is positive, down is negative, right? So our reference frame for 1D motion is horizontal, which means, you know, left and right, or vertical, up and down. Okay, so it's horizontal or vertical, one or the other. That's what we mean when we say 1D motion, and the number line is our reference frame. Does that make sense to you? Cool. All right. time. Time is one of those properties that's part of this whole motion business, because it's the one property that's always changing. It's always changing. And, you know, if we step out of the magical world of physics and think about it in our everyday life, you know, that's true. Time is all, you know, they say time waits for no man, right? Okay. But on a fundamental level, this idea of time and the, you know, the elapsed time between events is very relevant, because, for example, we might want to know, when is the next time the sun's going to come up? When is the next time, you know, this comet is going to be, you know, in our area? All of those kinds of questions, right? Events that happen in the physical environment can be quantified when we look at the property time. All right. And so when we want to talk about the elapsed time, or how long it took, or, you know, how much time passed, we use the symbol delta t. And we find delta t by taking the final time minus the starting time. And the unit for time or elapsed time is the second in the metric system. Okay. So if we want to know how much time elapsed, we find delta t. Now, typically, it's for convenience sake, you know, for simplicity, we a lot of times we take the starting time, or t naught, as 0. And so then if our starting time is 0, then we just say that the final time is equal to t. We don't have to keep using t final. If the starting time is 0, it's understood that delta t is equal to your t final. Okay. All right. So now we need to take a look at some other properties that we measure besides distance and displacement. One of them is average velocity. Another is average speed. And now we have to come to some understanding of terminology, because in everyday language, people sometimes use velocity and speed to mean the same thing. In physics, velocity and speed are very different, and you have to be careful to not only state the terminology correctly, but find it correctly, measure it or quantify it, calculate it correctly. They're very different properties, okay? They don't mean the same thing. So average velocity is displacement divided by elapsed time. Okay. And what we're assuming there is the starting time is 0, like we typically do. So if we take delta x over delta t, that is average velocity. Okay. If your starting velocity, if your starting time is 0, then you can just say delta x over t. All right. But in the, like broader sense, what if your time is not starting at 0? What if you don't start measuring the time until 3 seconds into the motion? Well, then to find the elapsed time, you have to say, you have to specify your start and final times. So delta x over delta t, we call that average velocity. Okay. And this average velocity involves direction. We'll get more into that next week. All right. Average speed, on the other hand, is distance divided by elapsed time. Okay. So see, that's why it's important from the start that you understand the difference between distance and displacement. Because if we want average velocity, we need to be using displacement. If we want average speed, we need to be using distance. Okay. For either of those properties, average velocity or average speed, the metric unit is meters per second. Meters per second. That's the unit that you need to be using if you're calculating average velocity or average speed. So if you're using meters per second for either of them, then it means what? You better know the difference in terms of what you're trying to calculate, because you can't rely on the unit. If I tell you, hey, this object's motion is measured using meters per second, that right won't tell you which property. But if I say, hey, I want you to find the average velocity, then you know the unit has to be meters per second. Or the average speed, it has to be meters per second. That's in the metric system, right? Because you know from your own experience, average speed, you know, your speed could be measured in things like miles per hour, kilometers per hour, feet per second, right? Inches per year, all that kind of good stuff, right? But we focus on the metric system, so meters per second. Instantaneous velocity and speed. Here's some more definitions or concepts that you need to, you know, let sink in, if you will, the difference between average and instantaneous. So instantaneous velocity looks at the velocity of an object at a particular instant in time, like freeze frame. You know, they used to do that thing back in the day, something mannequin challenge or whatever it was. And everybody moving around, and then all of a sudden there you just freeze. So at the moment you freeze, what is your instantaneous velocity? I mean, what is your velocity? Okay. So, you know, you have to imagine that you can measure the velocity when time stops, stand still for that instant. Okay. Instantaneous speed is an object's speed at any instant. Right. So it's kind of like what a cop does with the radar gun. When he clocks you, he's clocking you at a particular instant. At that moment, you were speeding. That's your instantaneous speed. Okay. Now, in this class, because we don't do calculus, if you need to be using the instantaneous velocity or speed, it has to be provided to you. Okay. Has to be provided to you. Acceleration is another property that we measure when we want to describe a moving object. Acceleration. So acceleration looks at the change in velocity over the change in time. So velocity is change in position over change in time. Acceleration is the change in velocity over the change in time. Okay. Now, what you have to be thinking about underneath that is, if the velocity is changing, then there are a couple of ways that could happen. I could, for example, hit the gas and that's going to change my speed. Or I could hit the brakes and that's going to change my speed. If I change my speed, I'm also changing my velocity. Okay. Now, the other thing that sometimes gets students is that you can also have a change in direction and have a change in velocity. You put your car on cruise control. What does cruise control do?
Keep the same speed.
Same speed, right? Now, you got it on cruise control. Drive around in a circle. What's changing? If I put it on cruise control and drive around in a circle, what's changing?
Direction, I guess.
Direction. Direction is changing. Okay. So you see, there's a clear case where the speed isn't changing, but the direction is changing, so the velocity is changing. If the velocity is changing, the object is accelerating. So I have to understand, how can I create, how does an object accelerate? Well, it could change its speed or its direction or both. Okay. Imagine riding in your car and you have to make a sharp turn, like you're in a steep curve. So one of the things you have to do is, I'm saying, like if you're a smart driver, a good driver, right? One of the things you do if you're going to get into this a sharp turn is you slow down, meaning what? You hit the brakes, but you also have to steer the wheel. So your direction is changing. So in that instance, your direction is changing and your speed is changing, which means you're definitely accelerating. Okay. And then they talk about instantaneous acceleration. We don't even have to get into that here. We don't focus on instantaneous acceleration. If we're using acceleration, you'll see in a minute that it's going to be fixed. So it'll be a known value, either is given or you can calculate it. All right. So we don't focus on instantaneous acceleration or average, because average implies that you got to start in the final value, but we don't get into that in here. An important thing that we do get into is, what units do I need if I'm measuring acceleration? All right. Anytime I'm measuring acceleration, my units have to be meters per second squared. Meters per second squared. Remember, we're doing metric system, SI system, System International. SI units for acceleration, meters per second squared. Okay. All right. Acceleration versus deceleration. I don't even like there to be a distinction. Why? Because I don't want you using the word decelerate in here. That word should not be part of your vocabulary in here. It's explained here because it happens. People use the term, and you need to understand what they mean when they say deceleration. But in physics, we only say an object has an acceleration, and that acceleration can be positive or negative. And we understand positive acceleration. It means the object is speeding up. But typically, if the object is slowing down, we say it decelerated. Don't say that. So the object had a negative acceleration, slowing down. So we're going to keep it as simple as that. We don't need all these exotic combinations. If the object is speeding up, the acceleration is positive. Hit the gas, speed up, your acceleration is positive. Hit the brakes, slow down, your acceleration is negative. So acceleration can be positive or negative. Positive acceleration, that's an easy case to understand. The object is speeding up. Negative acceleration, the object is slowing down. So let me see who's got their thinking caps on. I have an object that has a positive acceleration. Is its final velocity going to be bigger or smaller than its starting velocity? Anybody out there?
I'm gonna take a guess and say bigger.
Why? What? let me ask you something. And we need to have an honest conversation here, because no, you were the only brave soul that opened the mic. And so I give you, you know, like, I respect that. But let's talk about why you were guessing. If your object is speeding up, meaning the speed is getting bigger, right?
Correct.
So if that is the situation, and I ask the question, will the final velocity be smaller or bigger than the start? If you're speeding up, it has to get bigger, right?
Correct.
Right. So see, that's where I tell people, don't throw your everyday experience out the door, because somewhere in there you get that. You hit the gas before in your vehicle, right? You know that if you're looking at that speed gauge, when you hit the gas, it goes up, right? So that means your final has to be bigger. Okay. And if your final is bigger, your acceleration is going to be positive. Now, let's talk about the opposite scenario. So that means that if you hit the brakes and your speed gauge goes down, then your final has to be bigger or smaller. Question, bigger or smaller?
Smaller?
Huh? I
Smaller?
didn't hear.
Smaller?
You said smaller?
Yes, ma'am.
Okay, I'm sorry. I thought you were saying hello, like your audio wasn't working, but smaller, right? You hit the brakes, your speed gauge in your car goes down. It means that your final has to be smaller. And in that case, your acceleration is going to be negative. Okay. So we're going to only focus on those two extremes. Hit the gas, speed up, acceleration positive. Hit the brakes, slow down, acceleration negative. Now, what we want to do here in this section is we want to focus on a very specific type of 1D motion. So the definitions that we've looked at so far, position, displacement, distance, speed, time, acceleration. So far, the definitions that you've seen work for any type of motion. But now we want to take those definitions and look at a limited case of 1D motion. Okay, so we want to restrict our object. Right? Our object can only move in a certain way. And the way that our object is allowed to move is with a constant acceleration. So the object is in motion, but it's moving with a constant acceleration. Okay, now let me see who's really thinking out there. If the acceleration is constant, is the velocity going to change?
Oh.
I gotta know.
-2.
2. I got 2 no's.
No.
Got 3. So for those 3 brave souls that spoke up, and I can't see the class while I'm sharing, so I don't know who's responding. That is incorrect. And let's see why. Because you just told me if there's an acceleration and it's positive, it means the object is speeding up. So the velocity can't be constant if it's speeding up. Likewise, if the acceleration was negative, always the same negative value, that's what constant means, right? If the acceleration was always the same negative value, that means the object is slowing down. That also means the velocity has to change. So constant acceleration does not mean that the velocity is constant. Constant acceleration means the velocity is changing uniformly over time by the same amount each time. Okay? This is where it's critical that you know the difference between velocity and acceleration. Okay? Constant velocity means the acceleration is 0. If the velocity is constant, your speed is staying stuck. Okay? For when we're talking about linear motion. Okay? If the object is moving in a straight line and the velocity is the same. So you're on cruise control going in a straight line. Cruise control means what? Your speed is not changing. If your speed is not changing, how much are you accelerating?
None.
None, right? Okay. Now let's take it a little bit deeper. Let's say your acceleration is something besides 0, but it's constant. That means that acceleration isn't changing. If the acceleration is constant, think about it. You always got your foot on the gas, getting bigger, but by the same amount over time. Does that make sense to you?
Yes, ma'am.
Yeah, okay. See, that's why it's important that you get inside these definitions and bring your experience to the table. You get the idea of accelerating. If you're accelerating, your speed has to be changing. Okay. If you're not accelerating, your speed is not changing. Okay. So think of it in, like sometimes if you get a little bogged down, it helps to stop and say, okay, wait a minute. Let me apply this to a real situation. What's really going on here? Okay. That's the thought process that has to be there when you're analyzing motion. Okay. But you can see very clearly, if you don't understand the difference between acceleration and velocity, and I ask you to calculate something, that's going to be a problem, right? You have to know the definitions and the concepts to apply them correctly. Okay. All right. So now they give an example of a motion where there's always constant acceleration, and that's called free fall. Okay. They're talking about that familiar example with gravity. Okay. And when an object is moving under the influence of gravity only, it has a constant acceleration. All right. So we'll see how that works here shortly. All right. So what you see here on the screen is a set of equations. Now remember, I said we restricting our motion, right? So we only focusing on objects that move in one dimension. Think about it, horizontal or vertical, one dimension with constant acceleration. So we really watered down our situation here. Our object can only move in a straight line, and it's moving with its acceleration fixed. Okay. If that is the scenario that we're dealing with, then the only thing you need to describe the motion are these equations. These 5 equations are the only thing we need to kinematically describe our moving object that is moving in a straight line with a constant acceleration. Okay. So see, if we can get it down simple enough, we can do some things to understand the motion. Now, you might be looking at these equations going like, yeah, right. You expect me to use that? No, not really. I expect you to know what they are. These are called the kinematic equations of motion. And they only work if the object is moving in one direction, one dimension, with a constant acceleration. Okay. But we'll see here the equations that you're going to have to use to solve problems are going to be much easier than what, I'm going to frame it in a way that is much easier for you to deal with. But no matter if you use these equations or the ones I'm going to give you, the light version, I always say the kinematic equations of motion light. Kind of like you have light beer, right? I'm gonna give you the light version of these equations. And it doesn't matter whether you use this one or mine. If you don't understand the difference between velocity and acceleration, and you don't understand the idea of position, then it doesn't matter what equations you have. You won't be able to adequately solve problems, okay? So I don't need you to memorize these equations at all. In fact, I don't even require that you have to use these equations. Now, for those of you who like, if you really put the time in, you will find that these equations are very beautiful and very elegant in terms of what you can do to explain the motion of an object that's moving in one dimension with constant acceleration. In other words, if you learn how to use these equations, you got it. There ain't nothing I can't touch you with a 10-foot pole if you know how to use these equations. But I'm going to give you the light version that if you understand them, you'll be able to do the kinds of things that you need to do for this class. Okay. And we'll see that here. All right. So now let's restrict our motion even more. So one dimension, constant acceleration, free falling. So free falling means vertical motion only. Okay. So our object is moving vertically. And remember, vertical could mean up or down. What makes it free fall is moving vertically under the control of gravity only, no air resistance. So that's your scenario when we deal with free fall. It's moving vertically, up or down, but the only thing controlling it is gravity. And what gravity does to that object that is free falling is it accelerates it. And it always accelerates it by the same amount, 9.8 meters per second squared down. That's why when you throw the ball up, it comes back down. Why? Gravity. Gravity makes it come back down. How much? Acceleration. 9.8 meters per second squared down. Okay. Free fall. On Earth's surface, 9.8 meters per second squared. And since this is an acceleration, down. Because we're taking down as our, direction in this case, because that's the way gravity points for our purposes, right? Okay. So it's very nice then if you think about that, because you are dealing with motion where you know the value of the acceleration. You don't have to solve for the acceleration if it's free falling. If it's free falling, acceleration is given. How much? 9.8 meters per second squared down. So that means we can go back to these kinematic equations. Oh, sorry, scroll here. You can go back to these kinematic equations. If it's free fall, and everywhere you see A, everywhere you see an A, replace it with minus G. The G, because the value is 9.8 meters per second squared. The minus because it's down. So in the third equation, replace the A with minus G. In the fourth equation, replace the A with minus G. In the very last equation, replace the A with minus G. You have just adjusted the equations to account for free fall. The only other thing we do is we change the X to Y. So we like to use X for horizontal motion and Y for vertical motion. So replace your X with Y and replace all A's with minus G. Now you have the kinematic equations of motion for free fall. And if you're on planet Earth, how much is G? 9.8 meters per second squared, and it always points down. If you go to the moon, not going to be 9.8, about 1.7 meters per second squared down. But see, that's why they can, you know, they say one something step for mankind, one giant leap, or whatever they say. I don't know if some of y'all might know exactly what the words are, but you get the idea. It looks like they're able to take big giant steps on the moon. That's because there's less gravity there. Okay. All right. Go to Mars, about 3.75. Go to Jupiter, multiply 9.8 times 2.5. Okay. So free fall, gravity only, no air resistance. That's a real like what do you mean no air resistance? Right? Because I just told you, don't throw your experience out the door. All your life, if you think about it, all of your existence, in fact, all of human existence, in fact, all of anything existing, there's air. And now I'm telling you, imagine a world without air. But we do it because it allows us to simplify the motion in a way that we can get a really, really good description of what's going on. It's not total, it's not complete, it's not totally accurate, but as I always like to say, good enough for government work. Okay. What are your questions on what I mean when I say free fall? All right. So the next part of this deals with the graphical analysis of motion. And so that gives us another option, another way to describe our moving object, because we don't necessarily need equations to do it. They kind of go hand in hand. You could use the equation to make a graph, and you can look at the graph and tell what the equation looks like. And that's kind of exactly what you're going to be doing in problem set number 3 next week. So in fact, next week, you're gonna be looking at this graphically and utilizing my kinematic equations light. All right. So that's all for this packet. I'm gonna stop the share for a moment. It's right at 7 o'clock. We've been at this for a minute now. Let's take a 10-minute break and come back here at, let's say, 7:15. Okay, so I'm gonna cut my camera off And at 7:15, we'll come back and we'll resume our coverage of 1D motion. Right, so I'm gonna do a quick test to see if we can you can hear the audio on this video that I'm about to play. Okay, so
Grammarly does more than catch errors. With
will somebody kindly unmute and let me know if you're hearing that?
Yeah, loud and clear.
Okay, great. And you're also seeing it?
No, ma'am.
You were seeing it. You weren't seeing the video?
No, man. Just a ultra clear volume.
Okay. Oh, let's see. There we go. That's what it was. I had it on advanced options. No, now let me try it again. Are you hearing?
No, ma'am.
You're not hearing?
Not hearing, but seeing.
So you're seeing but not hearing this time.
Yes, ma'am.
Okay, let me see. Okay. Let me go in to that's not what I want. Okay, hang on. Let me stop the share and try it again. Bear with me for a second. That was my issue. I thought I figured out how to fix it. Nope. Okay, let me try it one more time. No, that's not what I want. Okay, there we go. Screen. This one. Oh, share sound. There it is. Okay. Okay. Are you seeing the screen now?
Yes, ma'am.
Okay. And let's see.
good, and this, or how about this?
What about hearing?
Grammarly helps you be concise. If your tone might make someone feel like this, Grammarly can remind you. It would.
Were you hearing the audio?
Yes, ma'am.
Okay, that's what I wanted to make sure, because I was trying to figure out if I hit the right button, because I thought I knew what I was doing. And so good. Okay. So now I'm just going to skip over that. I do apologize.
Welcome to the.
And so this video that you're going to be watching and listening to covers some of the different types of motion graphs that you'll utilize to help describe a moving object. Okay, we're not going to do all of them, just a few of the very basic ones. Okay, and if at any point you want to watch this again, all you have to do is go into the weekly overview under the required readings viewings tab, and you'll see motion graphs, and then you could click on that, and then you can come back and watch it over and over if you need to, but we're going to watch it now. That way I can kind of pause it at some key places, and we could have a little bit of a talk about it, and I can answer any questions that you might be having. Okay, so I'm going to start it again.
Video lesson on physics motion graphs.
Yeah.
The objective of this lesson is to understand the relationships of distance time, velocity time, and acceleration time graphs, and to be able to sketch those graphs for almost all the major types of motions that we'll see in this course. Let's start by taking a look at the types of graphs that we can draw and the information that we can get from them. We start with the distance or displacement or position, all the same thing with regards to the graphs. So distance, displacement, position versus time graphs. The symbol that we'll be using for distance, displacement, position is X, and the symbol that we'll use for time. So for us, the distance time graph will be an X versus T graph. What can we get from them? We can, of course, the easiest thing we can get is we can get the distance at any given time just by going down to the time axis, going up to the best fit line, and then over to the left, find out how far it's going, how far it's traveled at some given time. We can also get the average velocity from the slope of the straight line. These two keywords go together, average velocity and slope on a distance time graph. And we can also get the instantaneous velocity from the slope of the tangent line to the curve.
So that last point, number 3, we would not be having to find at this level of a course. You wouldn't have to calculate instantaneous velocity from a graph at all. Again, like I mentioned, if there's a need to use the instantaneous velocity value, it will be provided to you. Okay, so what you'll be concentrating on if you're using a distance versus time graph is the distance. Obviously, if it's a distance versus time graph, you can get the distance. But the other thing that you can calculate from a distance versus time graph is the average velocity. Okay, so just keep that in mind as you're watching.
At that point. So if our best fit line is not a straight line and it's a curve instead, you can see how we can't get average velocity from that because the velocity is changing, but we would be able to use a tangent line and get the instantaneous velocity using the slope of the tangent. And I'll demonstrate that for you later. Our next type of graph is the velocity or speed, and the same symbol we use for that is V versus time graphs, again T, so a VT graph. And what can we get from those? The easiest, of course, again, velocity time graph is the velocity at any given time. Similarly, we get average acceleration from the slope of the straight line. And one thing that is commonly tested is finding the displacement of the object by finding the area between the line and the time axis.
Okay, again, that third bullet under the velocity time graphs, we would not be doing, I would not ask you to find the displacement using a VT graph, right? If I wanted you to know the displacement in that type of scenario, I would have to give it to you, okay? So, you know, just be mindful of, you know, how we will use this information and limit it in a way that, you know, we accommodate the fact that we don't do calculus or any other higher level math that you would need to do number 3 kind of on either of those.
Okay, they really like to test that one. Okay. Our last type of graph is the acceleration versus time graph. Our symbol for acceleration is A, and of course versus T. So these would be AT graphs. And what can we get from them? Only the acceleration at any given time. They're the most limited type of motion graph that we can get as far as the information we can attain from them. And again, I'll demonstrate this for you as we start to do the various graphs for all the types of motion. Let's move on to that, and let's take a look at what we're going to do for each of these motion scenarios or situations. We're going to draw the XT, VT, and AT graph, one right under the other, so that we have a good understanding of the differences between the graphs and what they communicate to us. So we're going to start with an object at rest. We're going to start easy and work our way towards the harder scenarios. So for an object at rest, if an object is just standing there, that means that its position wouldn't be changing. And as time goes forward, so you could pick any spot, and what this of course means is that the distance is not getting bigger or smaller as time progresses. Okay? Well, if an object is at rest, that means its velocity is 0, and where the time axis intersects here on.
So he just said something that's very valuable for you to understand in terms of motion. He gave you a scenario. The object is at rest. At rest is a term that means not moving. So if it's not moving, its position can't be changing. If it's not moving, then its velocity is 0. If it's not moving, then it's not accelerating. So its acceleration is also 0. Okay. So see, that's why I said it's important for you to take the concept and say, now, what would that look like on a graph? Okay. Or if given the graph, what is that telling me about the motion?
On the y-axis would be where where velocity is 0. So we would have a VT graph that has a horizontal straight line on the time axis. If there's no velocity, there's no acceleration. So it also has a 0 AT graph, a horizontal line on the time axis. Okay? We now go to an object moving at constant velocity away. What does that mean? That means the velocity is constant, but the distance is increasing over time. So this, of course, would be a straight line, sloped upward. And this, if you take a look, the X numbers are getting bigger while time is moving in a positive direction. That's the only direction time can move. Okay, and the fact that the line is straight means that the rate of change of the displacement or distance is staying constant, and of course that means constant velocity. If that's true, then on our VT graph, we're going to have some non-zero velocity over that same time interval, and it should be obvious to us that that velocity remains constant. You notice here that this horizontal line is above the time axis. The slope of this line is positive up here on the XT graph, so our velocity is positive on our VT graph. We still are not accelerating. This object is not speeding up or slowing down, so its acceleration value is 0. So this would be a horizontal line on the time axis. Moving on to our next scenario, object moving at constant velocity toward. Well, constant velocity means our line is going to be straight. Toward means that our X numbers, our distance numbers, are going to be decreasing. So this would be a straight line, negatively sloped, showing that our X value is decreasing as time is increasing. Straight line indicating to us that the rate of change of that distance is remaining constant, therefore constant velocity. Well, constant velocity again means that we're going to have a horizontal straight line. This time though, our horizontal straight line is below the time axis. The slope of this line is negative, indicating negative velocity, meaning that it's going toward. So the first lesson we pick up here on VT graphs is that when your line is above the time axis for a VT graph, that means the object is moving away from the point of origin. And when the line is below the VT graph, the object is moving toward the point of origin. Huge point for you to remember there. Our object is still not accelerating, so its A value is 0. So again, we have a horizontal line on the time axis at which A equals 0. Okay, next we go constant, object moving at constant acceleration away. That means this object is speeding up, and if it's moving away from the point of origin, that the x numbers, the distance numbers, are getting larger. This will result in a curved line that looks something like that, and curved upward means that it's getting faster. I'll demonstrate why for you here in a second. And away indicated by the fact that the x numbers are getting bigger as time increases. Okay, now why is this a curved upward line like this and not a curved upward line like I just demonstrated with the pen? Okay, if we take our tangent line, which I'm going to grab a tangent line down here and bring it up. We start out at the beginning here. Tangent line being a line that touches the curve only in one spot. You can see that at this particular spot, the slope of this tangent line would be 0. So this object had started from rest. However, when we go here and we draw our tangent line, now we have a positive slope for that tangent line. What does that mean? Positive velocity means the object has gotten faster. When we move upwards and higher on the graph, what's happening to our tangent line? Our tangent line slope is getting steeper. That means the speed is increasing. That means our object is accelerating. If we were to do the other line, and we'll have that scenario later, you would see that the slope would be decreasing, showing that the velocity is decreasing. Okay? All right, object moving constant acceleration away. So that is going to be a straight line on our velocity graph, positively sloped. And that would indicate to us, of course, that the velocity is increasing over at a constant rate, therefore constant acceleration. And as we reviewed earlier, it's above the t-axis, indicating to us that the object is moving away from the point of origin. Now we do have a non-zero A value, and because the slope of this line is positive, that would be positive acceleration. So whatever that acceleration would be the y-intercept for this line, okay, and a horizontal line above the t-axis because acceleration is positive. Going to our next scenario, object moving at constant acceleration toward, okay. This, of course, means that the speed is increasing, but we're losing distance getting closer to the point of origin. Okay, so this line would look something like this, slope downward. Try to draw a better curve than I can with my pen here on the screen. Okay, for the VT graph, sorry about that. For the VT graph, constant acceleration means we're going to have start from rest and get faster, so the V numbers have to be getting bigger, but we're moving toward the point of origin, so we're below the time axis. So our V number is getting bigger, but being below the line means our line is sloped downward like this. Notice that the V number is getting bigger, meaning constant acceleration toward below the time axis. Here we have a negatively sloped line. The slope of this is the acceleration, of course. So our acceleration would be a straight horizontal line below the time axis.
All right. So he gave you the different scenarios that we will encounter when using graphs to describe motion. If you recall, the very first graph that he went into was the distance versus time graph, right? Well, he started off by looking at an object that's at rest, and what do those graphs look like? And then let's take a look at a graph where the position or the distance is changing, and if it's changing uniformly, then you will have a velocity versus time graph that's linear, but the acceleration will be 0 in that case. Okay. And then, you know, he did the scenario moving toward, moving away or toward. And then he went to the scenario where now you have an acceleration, which means the velocity is getting bigger. Okay. And you know, moving away or toward. Okay. So those are the kinds of things that you need to be able to you know, comprehend in terms of the motion. So at rest, notice that the position is staying the same. The velocity and acceleration don't exist because it's staying in the same spot. That's what that first graph is telling me. The object is not moving. It's at rest. But at rest just means the position is fixed. And that translates into position fixed, no velocity, no acceleration. Okay. And then let's take it to another level. Now let's have, well, we need to go a little bit further. That the scenario where you have constant velocity, that means your position is going to increase uniformly, but your velocity is going to stay constant. You see that horizontal line on the VT graph means the velocity is constant. If the velocity is constant, your position, the XT graph, is linear. And it means then if your velocity is constant, you're not accelerating. So the AT graph has a horizontal line at 0 because you're not accelerating. Okay. And then he's looking at the scenario where you have constant velocity toward. Because if in the other position time graph, you're moving away, in this graph, the object is moving toward where it started from. It's coming back to where it started from, in other words. And so your position is decreasing. That means that your velocity is constant, but negative. And then again, that also means your acceleration is 0. Okay. So you see at each stage, you can take this one-dimensional, you can take this one-dimensional motion and, you know, increase the complexity. And then you must look at you must be able to translate that to the graph. Or if given the graph, can you tell me what's going on with the motion? Okay, the reverse scenario. Okay, so it does take some thinking about what's going on in order to correctly utilize the graphs. Okay, so you know, I don't typically have you calculate, you know, use the graph to calculate things, but I do like to use the graphs to ask you, based on this graph, what is the object doing? Okay. And then, you know, of course, he went to the final scenarios where you had a positive acceleration, meaning the object is moving away. Okay. That means the VT graph is linear. And now you have a value for A that's not 0. And then the last scenario, you have a, the object is moving toward with a constant acceleration. So you see that curve. When you look at a position versus time graph, if it's a curve, you know the object is accelerating, okay? And if the curve is going up, that means the object is moving away. And if the curve is going down, like in this instance, the object is moving toward, okay? And we say toward, meaning toward its origin point, okay? If the object has a positive acceleration, constant acceleration, that means the VT graph is going to be linear, but notice that because this object is moving toward, the graph, VT graph, the slope is negative, okay? And it's below the axis because our A is negative, okay? And then if our A is negative, that's what the last graph represents, the A being negative, okay? So those are the kinds of scenarios that you'll have to deal with when utilizing the motion graphs. So let me go back. Oh, sorry. Let me get back to the class screen here. So again, you can find this motion graph business here, right there in the required readings viewings. You can watch them as many times as you need to help you get a grasp on that whole, what does the graph tell me about the motion, okay? All right. Now what I want to do is I want to kind of wrap things up here by going into my extra notes. The very last item, extra resources, under the announcements. And if you click on that link, it opens up a folder. And in that folder are subfolders, one for each of the topics that we cover. And since we're doing 1D motion, look at all the great extra notes that you have available related to 1D motion. I love this one here. I wrote this on the board when I had a face-to-face class. And what I do in this particular screen is, oh, I'm trying to move the picture, but I need to scroll. There we go.
Are we supposed to see it?
Oh, sorry. Let me see what happened here. Hold on just a minute, because I'm trying to figure out what happened. Where'd my share go? Oh, there we go. My bad. I'm thinking I clicked on the share. Sorry. And are you seeing that screen now?
Yeah.
Okay. And I'll go into the 1D motion. Remember, these are extra notes, right? These are extra notes that I made available to you. And bear with me just for a second. Okay. And so, I think there's some great tools. Part of the reason why I don't have them in the notes of the required readings viewing is because there were things like when I wrote on the board in a face-to-face class and that kind of stuff that, well, they give me grief if I put it in the course, but it's some great resources. So I just put them out there in the announcements and you can use them as you need to, okay? I like to refer to them because, sometimes seeing these things in a picture format is better than me just talking about it. So, so you see on this screen, I define what free fall means for you again. But here's the thing that I do that's very helpful. And let me blow this up a little bit. Okay. So you see here, right here, you know, one of the things I told you that I would do is to kind of simplify this whole formula business, right? So remember I said I was going to give you the kinematic equations light. So what I did was I took the kinematic equation for velocity, acceleration, and time, and I put it in my problem-solving pyramid. Because you know what my pyramid does, right? It tells you whether you multiply or divide. You don't have to worry about the equation anymore. You just have to multiply or divide. So for example, if I want to find A, I cover up the A, and it tells me I have to take V final minus V initial divided by T. If I want A, that's what I have to do. The final velocity minus the starting velocity divided by the time. Okay. What if I want V final minus V initial? Then I cover that up and I multiply A times T. What if I want T? Then I have to cover up the T and I take V final minus V initial divided by A. Why? Because the V final minus V initial, and notice there's parentheses around it, right? That's why they kind of group together. So the V final minus V initial, and then divide by A. So you see, you don't need those 5 equations that I gave you. If you're gonna solve problems where the object is accelerating, this is the only equation that you need. Okay. What does that look like in a free fall scenario? Remember, I told you that in a free fall scenario, we know the acceleration, 9.8 meters per second squared if you're on planet Earth, right? So in your pyramid, take the A and replace it with G. Now, if G is always 9.8 meters per second squared, you don't ever have to solve for G. If it's free fall, you automatically know G. So see, G is a given if it's free fall. So that, if I ask you, you know, tell me the acceleration for an object that was dropped from the Empire State Building with no air resistance, you don't even have to solve anything. Because if it's free falling and I ask you for the acceleration, that's constant, that's given, that's known. You don't solve for the acceleration in free fall. Okay. Now, if it's free falling, I could ask you about the velocity and the time. Okay. For example, if I wanted the time, then I'd have to take VF minus VI divided by G. Or if I wanted to get VF minus VI, I'd have to cover that up and then multiply G times T, right? So if it's free fall, it just means it's one less thing that you have to worry about finding because you already know the acceleration. And so that's what, you know, this screen helps you to do. The only thing that I think is like something that you know, will have to really process in your mind is that if an object is dropped, see, most students know that if you drop an object, that's free fall. No air resistance. That you don't even have to worry about it. No air resistance, right? If we drop an object, no air resistance, gravity only, the starting velocity has to be 0. If I dropped it, how fast is it moving when it started? 0, right? Now, we do have other scenarios. What if I throw the object up or pitch it down? If I throw it up, it's still free fall once it leaves my hand. The only difference is it didn't start from 0. The acceleration is always what? 9.8 meters per second squared. But if I pitch it up or pitch it down, It just means the starting velocity is not 0, okay? So you have to ask yourself the question, if it's being dropped, and we put 0 in for VI, hey, we know two things now if it's being dropped. We know that its starting velocity is 0, and we know the acceleration G, 9.8 meters per second squared. So if it's being dropped, only two things I have to find, VF or T, depending on what the question asks, okay? Now, another thing I want you to pay particular attention to with this pyramid for free fall, and even this pyramid up at the top, if the acceleration is constant. Nowhere in my pyramid, no, this one or this one, do I ask you anything about distance. This pyramid has nothing to do with distance. This pyramid has to do with acceleration, velocity, and time. Okay? So you're either looking at an object that's moving horizontally with a constant acceleration or free falling with a constant acceleration if you're using these two pyramids. Okay? So that's my kinematic equations like. The only other pyramid that we use in this class involves distance. And you'll see that in just a moment when I solve some sample problems. Okay? All right. These two pictures over here are exactly the same. I don't know why it, yeah, it just doubled them. I don't know why I did that on those. This one is a nice visual because I show you how the units work for acceleration. Okay. So the question is, why are the units for acceleration meters per second squared? So let's see. To get acceleration, what do you have to do? You have to take VF minus VI over T. Well, if I'm doing VF minus VI, what unit am I going to get? Meters per second. Why? Because the unit for V is meters per second. What if I'm dividing by T? What unit am I going to be dividing by? Well, the unit for T is seconds. So I'm dividing by seconds. Okay. So you see right in here, I have meters per second divided by seconds. We'll work that out mathematically. Meters per second divided by seconds, that's meters per second times 1 over second. You learned in your time when you learn fractions, in order to, when you divide by a fraction, you have to multiply by its reciprocal. So I do meters per second divided by seconds over 1. I flip that over and multiply by the reciprocal. That becomes meters per second squared. So acceleration in the SI system has units meters per second squared. And you get that because you're dividing the unit for velocity by the unit for time. Okay. All right. All right. And so what I want to do now in this packet, and there's a nice little packet that deals with free fall. You can take a look at that one. There aren't any problems solved in there. This packet is where there are some sample problems. Okay. So I go back and describe, give some definitions. You can take a look at them. Okay. The only other pyramid we need. So look at, I took 5 equations. Sorry. Hold on just a minute. Sorry about that. It was my puppy barking. I wanted to see what was going on. Okay. All right. So as I was saying, the only other pyramid that you really need to focus on in this material is the pyramid that looks at speed, distance and time. Okay. They use this funny looking script, V for speed, D for distance, and T for time. And notice how they're related to each other. Speed equals distance over time, right? So I took all 5 of those equations that you saw in the notes, and I collapsed it down to 2 pyramids. One for distance, speed, and time, and the other for velocity, acceleration, and time. Right? So, hey, better to have 2 pyramids than 5 equations. Okay? So now, what kind of problems should you be able to solve using these pyramids? See, here's the one for velocity, acceleration, and time. Okay. So it says here, let's look at a couple of sample problems. Your neighbor skates at a speed of 4 meters per second. You can skate 100 meters in 20 seconds. Who skates faster? So now we know how fast the neighbor's going. The only thing we don't know is, well, how fast am I going? Well, I do know that I cover 100 meters in 20 seconds. So I can find my speed by doing what? Distance divided by time. But the nice thing is that I don't have to worry about it in terms of an equation. In my pyramid, if I want my speed, I just take what? My distance divided by time. 100 meters divided by 20 seconds, 5 meters per second. So the neighbor is only going 4 meters per second. I'm covering 5 meters per second. So that means what? I win, huh? I skate faster, or you skate faster, okay? Let me slow down. Any questions about this particular problem and the pyramid that I used? All right, because these are exactly the kinds of things that you would have to do in the problem set and, on, like exams or what have you, okay? So it says here, a roller coaster starts down a hill at 10 meters per second. 3 seconds later, its speed is 32 meters per second. So we can gather just from the way this question is stated, or the information is stated, that this roller coaster is speeding up, because we can see that it starts at 10 meters per second and then it gets bigger all the way up to 32 meters per second. How long does it take to do that? 3 seconds. So if we know the starting and final velocities and the time interval, we can find out how much acceleration. Okay. So we're given the start and final velocities, the time elapsed. So let's go to the pyramid. If I want A, I have to do VF minus VI divided by T. So VF is 32 meters per second, VI is 10 meters per second, and the time is 3 seconds. So you subtract, you get 22 meters per second, and you're dividing by 3 seconds. It gives you 7.3 meters per second squared. So this roller coaster is speeding up, and its acceleration is 7.3 meters per second squared. Okay. What are your questions about this example? This one got a little bit more complicated than just the distance pyramid, but is everybody comfortable with the calculation part of this?
Yeah.
Whole lot easier than using those five equations, right?
Yeah, I think so.
Yeah. Says here, sound travels 330 meters per second. If a lightning bolt strikes the ground 1 kilometer away from you, how long will it take for you to hear it? Let me ask you a question. What are they asking me to find when they say, how long will it take? Are they asking me for a distance or what? Time, Correct. They're asking me for time, right? I mean, if, you know, let's imagine somebody who's new to the neighborhood walks up to you and says, hey, how long will it take for me to get from your house to, wait, hold on. What happened there? Bear with me. I might have to stop the share and share again because something went haywire there. Oh, yeah. There we go. That's what happened. I closed it by accident. So as I was saying, imagine that, you know, there's somebody that's new to the neighborhood and they walk up to you and they say, hey, how long will it take to get from your house to such and such store? Well, if they're asking you how long it'll take, they're not asking you how far it is. They're asking you the time. How much time is it going to take, right? Okay. So that's why it's important when you read these questions, slow down for a minute and think about what are they asking me to do here? Because I have had a lot of students read a question like this on an exam and they think I'm asking them to find time, find the distance, because they read it and they say, oh, how long? How long? That means distance. But read it carefully. It said, how long will it take? That means time. Okay. So in this particular example, they give us the speed. They give us the speed for sound, 330 meters per second. And they tell me that the distance, you know, the distance is 1 kilometer, because it says 1 kilometer away from you. That's, you know, that's distance. But notice in this problem, they have to do something that you should know how to do by now, and that's convert. They have to convert the 1 kilometer to 1,000 meters. And that is because the speed is given in meters per second. You can't mix meters per second and kilometers. But if I convert it to meters, I can mix. I can use meters with meters, right? So be careful when you're solving problems that you pay attention and don't ignore conversions if they're needed. Okay. So in this particular case, since they're asking me to find time in my distance, speed, and time pyramid, I just cover up the T, and that means I take the distance divided by the speed, D over V. That's 1,000 meters divided by 330 meters per second. Now, you can use your calculator to do the number part of that. That gives you 3.03. And as far as the units go, you have meters on top and the meters on the bottom will cancel, and you're left with seconds. Okay. So, you know, the biggest trouble that I see students having, or the mistake that I see commonly, is out of the 2 pyramids, students will choose the wrong one. You only have 2: distance, speed, and time; velocity, acceleration, and time. So you got to read the question and see what things are they telling me about. It would make no sense to use the acceleration pyramid here because you don't have anything given that deals with acceleration. Okay, so slow down, make sure you choose the right pyramid. And if that's your issue, you're not sure which one to choose, then that means you got to go back and get clearly the difference between velocity and acceleration, the difference between speed and velocity, right? The difference between distance and displacement. So that's why having a strong conceptual foundation is required when solving these problems, because I can water it down to, you know, 2 pyramids, but if you don't understand the concepts, it doesn't matter. how long will it take a car traveling 30 meters per second to come to a stop if its acceleration is -3 meters per second squared? So let me see who's paying attention here. What is this car doing?
Slowing down.
Slowing down. If it's slowing down, the acceleration has to be negative. Okay, the acceleration has to be negative. All right. And so here's that how long will it take business again, right? So we know that means they're asking me for time. But this time, since I'm using acceleration, I got to go to my other pyramid, right? I can't use the distance pyramid to solve this. There's nothing dealing with distance in this question. So I go to my velocity, acceleration, and time pyramid. They want me to find time. So I cover up the T. It means I got to do what? VF minus VI all together. That's why there's parentheses, divided by A. So fill in. VF is 0 meters per second. How do I know it's supposed to be 0? What tells me that? What's the dead giveaway that my final has to be 0?
Stop.
Stop. Says it comes to a stop, right? If it comes to a stop, the final has to be 0. Okay. All right. So that means we have the final velocity minus the initial velocity divided by the acceleration. Now be careful in this type of problem, because a lot of times when students solve this type of problem, they're tempted to put the bigger number in front and do 30 minus 0. But see, that's not going to work here, because the car did not end up going 30. It ended up going 0. And if you flip them just so you can have the bigger number in front, then when you finish, your T is going to come out negative. And I always tell students, if your T comes out negative, either go back and check your math or pray. Because either you did something wrong mathematically, or we're about to have a really bad experience on planet Earth. Okay? Time shouldn't be negative. All right? So when we do 0 meters per second minus 30 meters per second, and you divide that by A, -3 meters per second squared, you get -30 meters per second divided by -3 meters per second squared. Okay? -30 divided by -3, +10. That's an integer thing, right? Negative divided by negative gives positive. And then meters per second divided by meters per second squared. Well, you have to think, I got a meters per second on top, and I've also got a meters per second on the bottom. It's just when I finish, I'll have a second left, right? One of those seconds on the bottom won't cancel out. And so that's how I get my seconds as my final unit in this question. Okay. All right. So those are some examples. The rest of this packet has a really nice part on graphing. Okay. So if I were you, I might take a look at that. You know, again, I don't mandate that you use these. These are just extra, but I find that the problems that they solve, you know, they do a really good job of breaking down what you have given, what, you know, formula, pyramid you're supposed to use, and then showing the math. And that's why I rely on them, you know, to kind of help here. But, you know, you know, you use what you feel you need. Okay. All right. So with that, I'm done. I'm going to stop the share. And I just want to ask if there are any questions at this point that I can answer for you. All right. Well, I want to say thank you for joining in tonight, especially to those students who were responsive and interactive and engaged in asking questions or answering questions for me and sharing with the class. I really do appreciate it. That does make the time, you know, we have to be together from 5:30 to 8:15. We might as well, you know, kind of make positive use of the time, right? And be engaged with one another. So you know, I always appreciate those students who step up and engage with me in the class. And so you know, thanks. I really do appreciate that. Just as a reminder, this recording will be available in a couple of days. Give me a couple of days to get it ready and post it under the announcements in the event you need it. Okay. All right. Any questions?
No.
No, man.
Thank you. All right. So with that, I'm going to stop the recording.